So I'm prefacing this video with a little explanation of why I got wrong, the questions that I got wrong in this run-through. So I went and did this exam for the very first time. They published it very recently. I hadn't looked at any of the questions. This is fall 2019, by the way. And I went through, and as you'll see, I got 6 questions wrong. I took it as close to, exam standard as I could. Use the correct amount of time, etc. And let's go look at the questions that I got wrong and why I got them wrong. So question 9, and I'm only going into the specific thing that was wrong with my own logic, not the whole question as a whole. So what I messed up here, we're checking for polynomial subspaces here. For number 1, I didn't notice that here. Take a look down here. So if we have some polynomial that's a member of our subset, such that p at 0 times p at 2 is equal to 0. In this case, this guy evaluates to 0 when x is equal to 2, and we take another polynomial that fulfills this case but doesn't fulfill. That is equal to 0 for this case, but not this case. If you add those two together, it doesn't just add the behavior together nicely. If we add these two, we get 2x minus 2, which when we evaluate it at 0 and multiply it by it evaluated at 2, we get something that is not 0. So 1 is not closed under vector addition. With all of these questions, all of these polynomial and R to the n subspace questions, you should be very skeptical whenever you see anything squared, unless they're like writing a polynomial out and it's got like t cubed or t squared in it. That's not what I mean. What I mean is this kind of thing where we have some value times some other value, and that's the condition that you're actually caring about. That's usually should be a red flag, but I didn't recognize that as a red flag. Okay, 12. This is a really annoying mistake that I made. So started off with the matrix, reduced it down here, and reduced it down in a way so that it didn't change the determinant and just made the rest a little bit easier to do. And I tried to pull out this 4 and then the matrix that the sub-matrix formed by crossing out the row and the column that the 4 was in. And whenever you have to do that, you have to put the sign in front of whatever term we're pulling out here. And we can find that sign by going plus, minus, plus, minus, plus. Although, if you look over here, I have a negative sign there. And that negative sign gave me a negative 4 instead of a positive 4. And that was that. 14, this was a little bit of a weird question. We have, so we're working in the space of all 3x3 matrices, which now I'm really recognizing more is, you can think of it as a 9-dimensional space, because for A, B, C, D, E, F, and G, H, I, you can vary all of those individually, and you're kind of moving through a different dimension in the space. And H is the subspace of all the 3x3 matrices consisting of matrices such that A times 1, negative 2, 0 is equal to the 0 vector. So we multiplied this out and saw that A minus 2B plus D minus 2E plus G minus 2H is equal to 0. And then I chose the correct answer. Because my correct logic at the time was that, okay, this is the condition that kind of defines our subspace, and so each one of these terms can be varied independently, although we'd have to vary them in we can't just add one to A because then we'll add one to this side. But all of these terms can vary, and so with this condition staying true, so therefore our subspace should be 6-dimensional because we have 6 different terms here. But then I came back after I'd gone through the exam the first time, and I was slightly more stressed out. And I reread the question, and I was like, well, this is ax equals 0. That should be the null space, right? And so the null space should be defined by the free variables in our thing. So instead of these 6, I was like, well, really, we can vary C, F, and I however we want, and that shouldn't matter at all. And we'll definitely still, fulfill this condition if we like add 1 to C or F or I. And I was wrong. So this is not really talking about the null space, even though it's ax equals 0. It's really asking how many different terms over here can you vary and stay within the subspace, which to me, like 2 hours after taking this exam, still sounds weird, because and that's not a perfect explanation, is what I'm saying, because you can still vary C, F, and I, but I'm thinking of it more as a weird kind of columns, a weird kind of column space. I don't really know how to explain it, but whatever you take from that, I was wrong. Going through. Okay, 19. This was a mistake in reading the question. Even though I learned how to do this whole inner product shenanigans today, I did the math right. I didn't read the question. They wanted the orthogonal projection of this polynomial onto the subspace spanned by 1 and t. We found that. We found that fine. But then what we did was, let's see, where is it? We found 6t minus 5, or was it 6t plus 5? I'm not particularly sure. But we found the correct orthogonal projection. But what we did was take what we were calling h, this function right here, and subtracted from it that orthogonal projection. And of course, they had an answer choice lined up for that. So read the question. And then 20. Oh, this one really bugs me. Because I generally like to think that I have a pretty good geometric understanding for eigenvectors and eigenvalues, etc. Let's first talk about why A is wrong. So 2 by 2 matrices A and B have the same eigenvalues with the same multiplicities, then A is similar to B. So I have this written out here, recognizing that similarity really means that there is an invertible matrix P such that you can write A as the diagonal D and then P inverse. And that's all well and good, but in order for this to even happen, A has to be diagonalizable. And so you can have two by 2 matrices that only have one eigenvalue. So they have the same eigenvalue, and let's say they have a multiplicity of 2, but there's only one associated eigenvector. So in MA 266, we would say that the matrix is defective. It's missing an eigenvector. So the total dimension of all of its eigenspaces isn't equal to whatever the algebraic multiplicity of that eigenvalue, and so it's not diagonalizable. You can't write this, so they're not similar, and that's ugh. But what bugs me more is that I didn't pick C, and overall I was extremely confused by C. But now it makes complete sense. Here we go. So there exists an n by n non-zero matrix A such that every non-zero vector in Rn is an eigenvector of A. And this threw me for a loop a little bit with the every non-zero vector being an eigenvector. But I even had this animation playing in my head of just, okay, so I'm going to have to draw this out. We've got our basis vectors, right? Take those basis vectors, multiply them by a factor, and what have you done? All of space has expanded by that factor. And what is an eigenvector? It's a vector on which a transformation only scales things. And since we just expanded all of space, like we're kind of zooming in, any vector is just going to be expanded by that same factor. So yes, all of R2 here is an eigenvector. And so the kind of equation for this would just be any matrix such that any transformation matrix A that's equal to lambda I, where lambda is the scaling factor, so the eigenvalue that all of these eigenvectors will share, and then I just refers to the do nothing transformation. So we're multiplying our original basis vectors by that factor of lambda. So there we go. Not a hard problem, but the test can get you. And yeah. Last one. So in total, got 6 wrong, which was more than I thought I got wrong when I ended the exam. But I think overall this was a kind of brutal final compared to some of the ones we've had in the past. Like some of the 2017 ones, well, either one or two of them, I'm not sure, are just walks in the park compared to this. In fact, most of the past finals are. So that's not a real excuse. But I actually, this is good, because for this question I do have an excuse in that I did the written homework for this one today, but I didn't fully read the textbook. I was working a little bit ahead, so I kind of sort of forgot, and I'll walk you through what I forgot. So I knew that the orthogonal matrix Q that satisfies Q transpose times A times Q is equal to this guy will be composed of the normalized what are they called? The normalized eigenvectors, the normalized basis vectors for the eigenspaces corresponding to these eigenvalues here along that diagonal. So we found those basis vectors perfectly fine. In fact, it's this one, and this one. But what I forgot to do is, need to back up yet again. With these matrices, with a diagonal matrix, it's guaranteed that all of its eigenspaces, all of its eigenvectors coming from different eigenspaces are orthogonal to each other, but it doesn't guarantee that eigenvectors within individual eigenspaces are mutually orthogonal. So the two eigenvectors corresponding with lambda equals 4, if you take a look at them right there, those are not orthogonal. And I should have recognized that and then used, like a single step, Graham-Schmidt process, whatever, and gotten this vector right here. That's what we would have ended up with. But I did not know that was a thing you had to do. But that's not a very good excuse, because it's telling us to find an orthogonal matrix. This matrix was just straight up not orthogonal. These two are orthogonal. One and the first and the third columns were orthogonal, but 2 and 3 are most definitely not. Okay, so there's a little walkthrough for what I got wrong, just so that when you are watching, if you even choose to do so, I think this bit was more helpful than the 2 hours of suffering after this. But hopefully, if you do choose to watch the rest, you'll know when to close your ears and not listen to what I'm saying. So this video is different from every single other video I've ever uploaded in that I haven't seen this exam at all. I don't even have the answer key downloaded for it. This is the fall 2019, so the most recent final exam for MA 265 if you're taking the course with me this spring. And we're going to go through it as if it's a real exam. Looking at the questions for the first time, we'll see how well I can do here. I'm going to. I have my audio recording on my computer, so I've got the time there. We're going to give ourselves the full 2 hours and see how it goes. If you want to kind of take this along with me, I'd recommend pausing at the beginning of every question, trying to work it out, and if you've got it, then either watch me get it right or wrong, doing the same thing as you, or just skip ahead. But I think the important part here is going to be how, and this is true for all these exams, how you use your time that you have left over once you get through the exam the first time round. So usually it takes me about an hour to get through the 25 questions, and then after that, however we distribute that time that's left is going to be what actually matters. So let's, without further ado, let's get going. It's been 1 minute and 47 seconds. I'll just subtract that from the 2 hours to make my life a little easier. Okay, question 1. Given that the determinant of this matrix is 120, what is the determinant of this? Okay, first off, let's transpose this matrix. We're going to be working up from this matrix. Actually, no, let's work down from this matrix to that matrix. It'll be a little easier. So if we transpose that top thing, we'll get 2, 2, 10, DE, 5, F, and A plus 3D, B plus 3E, and 5C plus 15, 15F. Okay, that determinant. And we know that taking the transpose does nothing to our determinant, so we don't have to change anything. We also know that adding a multiple of a row to another row does nothing, so our determinant is still 120 if we remove this. Well, I got to be careful here. We will remove the 3 times D that's been added into here, but we're still left with we still kind of have this plus 5F here. Well, no, actually we don't. Okay, we can be safe and remove that. Okay, so now we have to divide our first row by 2, so that will leave us with 120 times 1/2. That'll give us the 115 that we're looking for. And then let's divide column 3 by 5 times 1 over 5. So 1 over 2, 1 over 5. That gives us our 111. Now we want this on the bottom, so we have to do that switcheroo, and that'll leave us with our A, B, C, D, E, F, 111, and that's 120 over 10, so 12, and we switch 2 rows, so times -1. So we get -12. I'm relatively confident about that. Okay, doing good on time. I say after the first question. Okay, let A be an m by n matrix and B be a non-zero vector in Rm. So m by n, so we're dealing with the output space of the transformation represented by A. Okay, that's good to know. Which of the following statements must be true? If AX equals 0 has only the trivial solution, then AX equals B has no solution. No, because if AX equals B, if AX equals 0 only has the trivial solution, that means that our matrix is full rank, or that it is that it spans the output space. And since AX equals, spans the output space, but only has a trivial solution, so I'm pretty sure that implies that our transformation is 1-to-1. So AX equals B, Yeah, and since B should be in our output space, then okay, I'm mostly certain that this is wrong, but we'll come back to it if that is an issue. Okay, if AX equals B has exactly one solution, okay, then A is an m by n matrix with m greater than n. Let's think about that. So, no, that doesn't have to be true. Let's think about it, because if we have an n by n matrix where m is equal to, okay, but they have that case in here, m equals n, because all m by n matrices where ax equals b has one solution are invertible matrices, and so it's a one-to-one and an onto transformation. What if n is greater than m? So that's the only case where they say that this wouldn't be true. If n is greater than n, that means that our input space is higher dimensional than our output space. Okay, and then yeah, I think this checks out. Yeah, because if you're transforming from 3 dimensions down to 2 dimensions, so you're going from all of R3 down to a plane, by definition, you have to smush some vectors, some line of vectors, onto a single point on that plane. And that should hold for all other dimensions that we're thinking about. So 2 should be good. If ax equals 0 has infinitely many solutions, then ax equals b has infinitely many solutions. So I'm thinking about transformations that end up that are not full rank. So we have our rank is less than the number of columns. So if there is a solution, oh, okay, so this is a little tricky, but I think I get it. B can be any non-zero vector in our output space. Let's take that same transformation we were thinking about from R3 down to a plane in R2. For any vector b where ax equals b has a solution, has an input vector x, then yes, you would have infinitely many solutions. You would have the entire line of vectors that all got squished onto that single point on the plane. But if you choose any point, any other point in your output space as your b, then there will be no solution. So this would be true if it's had either infinitely many or 0 solutions. So 3 should be no good. And 4, if A is an n by n square matrix, then ax equals 0 has exactly one solution. Ooh, they're being tricky here. Okay, so n by n square matrix, you would think, if you don't think about it enough, you might go, okay, and square matrices are invertible, and so an invertible matrix only has the trivial solution for ax equals 0 because its null space is 0 dimensional. But that's untrue. This only works if our matrix is invertible, but here I can give you an n by n matrix that's not invertible. That's not particularly invertible right there. So that should be false. So our answer should be 2 only. Okay, that question took a while. Okay, 3. Given that this is A and that's B, what is A inverse times B transpose? Okay, let's just compute it. I'm not going to think about whether or not there are easier ways. 1, 0, 0, 2, 1, 0, negative 1, 3, 1, multiplying by 1, 2, 3. Oh, but we need the inverse of A. U. Yuck. Huh. Okay, I guess we got to compute a 3 by 3 inverse. So finding the inverse of this, we need the determinant. We can take 1 times the determinant of, no, we can't do that. No, we can't do that. Okay, let's just do the whole thing. So we have this 1. We can say 1 times the determinant 1, 0, 3, 1, minus 2 times the determinant 0, 0, 3, 1 here. So that's going to go to 0. And then this other one, minus 1 times this sub matrix, that's also going to go to 0. So our determinant is just 1 times 1. So The determinant of A is 1. That's good to know. Ugh. Do we really have to compute all this? I really hope not. I really hope not. Inverse of the transpose. Yuck. Or wait, can we... No. I think we just have to do it. Oh, God. Okay, so we're dividing all these by -1, and then finding our cofactors. We'll get 1. Here we get 0. Here we get 0. Right here we get -2. Here we get +1 and 0, and then 6 plus 1 is 7. Sorry, I'm not talking too much. This is, we're not really explaining what's going on. -3 plus minus plus minus. Okay, and then +1. Yuck. Okay, and we divide all that by our determinant, and then take the transpose, and that's our inverse. So our inverse is actually has a 7 here, a -2 here, and a -3 here, with zeros here. Okay, if I did that right, taking this and transposing our result should give us our answer. This is a 3 by 3. This is a 3 by 1, so we will get a 3 by 1 out, which makes sense because we're getting a 1 by 3 as our answer. So 1 minus 4 plus 21. 1 minus 1 minus, that's 1 minus 4 plus 21. See, if testing gets you, we have a -3 plus 21 is 18. Okay, ooh, sweet, there are answer choices with 18 in them. If that was not any of these first ones, I would go back and reconsider my life choices. Okay, we get 2 and -9, so -7, yes, it's matching up. And then 3. 18, -7, 3. Okay, I'm assuming what I did was right because we got a correct answer. For now, we're going to move on. 4, suppose that this is an orthogonal set and x, y, and z are not 0. Okay, we're just going to throw back to Calc 3 right here and take a cross product. We're going to do I, j, k, and we are crossing 1, -3, 0, and 3, 1, -1 to get the mutually orthogonal vector to both of these, and then we can just look at its multiples to figure out any of this. So that will give us our first cross gives us 3, our second cross gives us 1, and our third cross will give us 10, right? 1 plus 9, yeah, 10. Okay, sweet. And then they're asking which of the following is true if we represent this as x, y, z. Which of these fractions works out? X over z, 3 over 10, that checks out. X over z. Oh, yeah, okay. And then y over z, nope. Y over z, nope. Okay, that should work. 5, let this linear transformation from R3 to R2 be a linear transformation, and S be a basis for R3 where those are our basis factors. What's the standard? Oh, don't want any Reddit notifications. What is the standard matrix for the linear transformation L relative to the standard bases on R3 and R2? Okay, this is 100% one of my weak points. So yeah, standard matrices for transformations relative to bases. Okay. So we know that our transformation is going from R2 to R3, so that makes sense. And these vectors here should be where Like this is where the first basis vector in R3 lands, this is where the second basis vector, and that's where the third basis vector in R3 goes. But past that, let's think about this. Okay, I'm going to skip this one. We're going to come back to it. 5 questions in, 15 minutes in. We're doing okay on time. So V is a vector space spanned by the vectors u, v, and w. Which statement is true? U, v, and w must be... Nope, they don't have to be linearly independent. V could be like a one-dimensional vector space, and they could overlap each other but still span the space. So nope. The dimension of V must be 0, 1, 2, or 3. Yeah, I would agree with that because whatever it's called, the spanning set theorem, tells us that the highest dimension that we can span with 3 vectors, if they're all linearly independent, would be 3 dimensions. So I would agree with that. And if they're all the 0 vector, then we would just span 0 dimensions. So yeah, I think that should be it. U, v, and w form a basis. Nope, we don't know that they are linearly independent. If V is R2 and W is just redundant, then no, they don't form a basis. The dimension of V, no, we don't know any of that actually. It could be 3 if these were like 1, 0, 0, 0, 1, 0, and 0, 0, 1. Then that would work. Then they would. Then our dimension of V could be 3, and everything would be fine. Okay, so B should be it. 7, let's find all real numbers k such that the parallelogram with vertices here has area 6. Okay, let's write this out because this should just be a determinant in the end. So we have 0, 0 as a vertex. We have 2k as a vertex. We have 4, 5 as a vertex. Should really be more like 4, 5 as a vertex, and 6k plus 5 is a vertex. So the distance, the y distance here is 5. The x distance here is 4. And so what does that tell us? Well, the area of a parallelogram is just base times height. How can we express this as a determinant? Let's see. Well, okay, here we go. The places that we move the basis vectors in R2, so let's say that our first basis vector got moved from 1, 0 to 4, 5, and our second one got moved to 2k. That's what should span. What spans in between here is, you know, the area, yeah, the determinant, essentially. So if we set up 2k, 4, 5, and solve this determinant for 6, we'll get 10 minus 4k is equal to 6. Although wait, nope, I gotta fix this because this should be our first basis vector. This should be our second basis vector. Yeah, because we want an area of positive 6. If we had you know, a negative determinant, then we would assume that those two had flipped. So it really should be 4, 5, 2k. So 4k minus 10 is equal to, oh god, stop emailing me, please, is equal to 6. 4k is equal to 16k is equal to 4. But here we go. So if we're thinking about, maybe we were on the right track, because if they want us to be thinking, I gotta plug my computer back in. There we go. There we go. If they want us to be thinking about just the area of the parallelogram, then we can also have a determinant of -6. And that should be good. So that wouldn't really be negative area, quote unquote. So if we solve that, 4k minus 10 is equal to -6. Solve this determinant that way. Then we'll get 4k is equal to 4k is equal to 4, so k is equal to 1. Yeah, okay, that seems to check out. So k is equal to 1, k is equal to 4. I'll go with that for now. 8. There's A. Which of the following statements is true? We're looking for a basis for col A, the column space of A, or the null space of A. So let's take A and row reduce it. We have -1, -3, 0, -4, -6, -1, 4 negative ones and a -3. And then we have 2, -1, 2, -4, 0. Oh, there we go. And this is, okay, grab a copy of it. Let's change the signs in row 2 and add it to row 1. We'll get 0, -2, 1, -3, -3. I'll flip the signs again just to make things mostly positive. Let's subtract 2 row 2's from row 3. That'll give us 0, -3, 0, -6, -6. So we can turn this into a 0, 1, 0, 2, 2, 2, 2, like that. And what can we do now? Let's subtract 2 row 3's from row 1. We will get 0, -1, -1, flip, flip, flip. 0, whoops, I already forgot what I erased. Yeah, 0, 0, 2 there. And what else? Let's subtract row 3 from row 2. That gives us a 0 here, a -2 here, and a 0 here. And it looks like, yeah, we are fully reduced. So let's put the rows where they belong. So we have 1, 0, 0, -2, 0, 0, 1, 0, 2, 2, and 0, 0, 1, 1, 1. There we go. So our free variables are x4 and x5, but let's just check for our column space. So we have a pivot position in the first 3 columns. So the basis for col A should be these 3, and that checks out right there. Ooh, but is B a basis for col A? I don't know. Man, I'm not sure. Oh God, there's a lot to check here. Okay. Yeesh, we're almost 30 minutes in. Is that a basis for col A? I'm gonna go out on a limb here and say no. I mean, what they've always showed us, at least, is that the 3 rows that the 3 columns that you get pivot positions in, you then go back up to A, and those 3 columns, or in our case 3, are definitely a basis for col A. So I'm going to say that this is false, but then we have 2 different null spaces to worry about. Oh God. Okay, let's solve for our null space though. So we'll have an x3 vector and an x4 vector and an x5 vector, and we get 2, -2, 1, 1, 0, and wait, 2, -2, -1, 1, 0, and then we should also for x5 get 0, -2, -1, 0, 1. So I would agree that this is definitely a basis for null A, but is D also a basis for null A? Well, what have they changed here? They've flipped some of the signs, and they flipped some of the signs for D for the first vector, and they've also flipped some of the signs for the second vector. This bugs me because I feel like we didn't go over this. Let's check E though, just to make sure. I kind of don't want to. Yuck. Well, okay, since we can do it in a little bit of a cool way though, because since we know that these first three columns form a basis for the column space of A, then instead of AX, we should just be able to do -1, -2. Sorry, -1, -1, 2, -3, -1, -1, 0, -1, 2, and multiply that by 5. And solve that equal to 5, 2, -8. Let's see if this works out. Let's flip all the signs here. Add row 2 to row 1. 0, -2, 1, 3. Subtract 2 row 2's from row 3. 0, -3, 0, -4. Flip these signs. What else? What else should we be doing here? Let's change this into 6, 8. And make this -6, 9. Okay, that's interesting. And then add row 3 to row 1. That'll give us 0 and 17. And then subtracting row 1 from row 2, 0 minus 19. And then let's see, this is 1 and 8 over 6. And okay, so we could subtract row 3 from row 2, and yeah, it would be consistent. We would get 3 pivot positions on our left side. Okay, interesting. I'm going to come back to this one. I feel like we'll be able to think about it a little better later. Okay, 9. Let P3 be the space of all polynomials of degree at most 3. Which of the following sets are subspaces of P3? The set of all polynomials in P3 is such that P0 times P2 is equal to 0. Okay, that's interesting. Then the set of all polynomials such that P1 is 4P0 plus 2. And the set of all polynomials P in P3 such that P1 is equal to 0 and P4 is equal to 0. Okay. Polynomial subspaces are a little bit tricky. Okay. Let's see. Let's check for including the 0 vector. Do these three include the 0 vector? So 1, P at 0 times P at 2 is equal to 0. Well, that is only true if either P0 or P2 is equal to 0. So that does include the 0 vector. That's good. What about 2? P1 is 4P0 plus 2. That doesn't have to include the 0 vector in any way. No. So I think 2 is already out. And then for 3, P1 is 0 and P4 is 0. Well, they're just saying that those entries are equal to 0, so that is good. So we're down to B, C, or E. Yeah, okay. So the other things we have to prove is closure under vector addition and closure under scalar multiplication. The only problem is, so like for 3, we don't know anything else about those polynomials, so I might have to resort to just using an example polynomial and just going through like that. So What's a polynomial where p at 1 is 0 and p at 4 is 0? Well, x minus 1 and x minus 4 does the trick. So x squared, yeah, and this is a subspace of P3, so that works. X squared minus 5x plus 4 is equal to 0. That works out for 3. So if we use that as a test case, then if we take two elements and oh, it's a set of all polynomials, so I kind of need another one. Or okay, let's test scalar multiplication. If we multiply this thing by 2, is this still true? Well, yes, because we could just write this up here, and this still, if we set this equal to 0, we can just divide that divide that 2 out, and we're good. So scalar multiplication is a-okay up there. What about 1, a polynomial such that p0 times p2 is equal to 0? That's interesting. Let's see. That would work for that polynomial right there. So x squared minus 2x. X at 2 is 0, and x at 0 is 0. And yeah, multiplying together, you still get 0. That would work under scalar multiplication. Yeah, any p0 times p2 times any constant will still be 0. So pretty sure that works for scalar multiplication too. What if we take two polynomials that this works for and add them together? What if? So another polynomial that has the properties that we want for number 1. Sorry, I'm going all over the place, kind of checking back and forth. This is not a particularly good strategy, I think. Will that still be true? Okay, well, the polynomial x works because x at 0 is 0 and x at 2 times x at 0 is also 0. So if we do some vector addition, we add these two together, it still should have the same property. So x plus x times x minus 2. What is this thing at 2? Well, it's going to be equal to 2. And what is it at 0? Oh, it's still equal to 0. So I have a hunch that this will work for vector addition. But it's not a very, very good hunch. Then for going back to 3, we have to test vector addition. Oh, God. P1 at 0, P1 is 0, P at 4 is 0, so we know it works for this. What's another vector that would work for? Aren't many of them. I mean, we can multiply the whole thing by x. That would still work. Yeah, that would just add another root for 0. So then if we add this to that, yeah, it'll still have the same properties. I'm pretty sure it's 1 and 3, but this is ugly, and this tells me I should really review that again. Okay, suppose A and B are n by n matrices. Which of the following statements must be true? A, B is equal to B, A. Okay, so first off, just because something's an n by n matrix doesn't mean it is invertible. And unless A and B are both the identity matrix, or maybe just one of them is the identity matrix, then this would work out. But we don't know that they're the identity matrix, so this should not be true. What else? What's going on here? If AB is equal to I, then B is the inverse of A. So that comes off as true the first time I read it, because we know that A A inverse for some arbitrary invertible A is the same as A inverse A, which is the same thing as I. So, and I don't know of any other cases where that would be the case. Yeah, and we can think about it geometrically too, because an invertible matrix is really the matrix that undoes, that does the exact opposite of the transformation encoded by the matrix whose inverse we just had to take. So doing multiplying a matrix by its inverse is the same thing as transforming and then doing the opposite of that transform. And so we're just left with the identity, which is do nothing. So that should be true. If A and B are invertible, then AB inverse is, nope, that's not true. It would be B inverse A inverse. We have to flip the order. So C is not true. 1, 2, 3, 4, 5, 6, 7, 8, 9 is invertible. I don't particularly want to check. Let's look at E. If AX equals B is consistent for some B in Rn, then A is invertible. No, it would have to be consistent for all B and unique for all B in Rn, so that's no good. Can we quickly see whether or not this thing is invertible? Because it seems kind of unlikely that 1, 2, 3, 4, 5, 6, 7, 8, 9 just happens to have a determinant of 0. Let's row reduce it. That'll do it. 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's subtract 4 row 1s from row 2. That gives us 0, minus 8, negative 3. Minus 12 gives us negative 6, so this can go to 1, 2, 0, negative 1. Subtracting 7, so we add 7 here. 16, okay, there we go. There's our 1, 2, so this becomes a 0, 0, and thus it can't be invertible. Done. 11, which of the following statements are true? 6, 1, 5, 3 is the subspace of the 2 by 2 matrices spanned by, oh god, wait. Not exactly sure how to do that. Subspace of the matrices spanned by those two. Oh god, this is kind of brutal. 2, the polynomial there is the subspace of polynomials of degree at most 3 spanned by those two. Okay, well we can work with that. Let's express these as vectors. So we have the constant, then the t squared, then the t cubed in that order. So we have 0, 2, 1, negative 1. Then our second one is 0, negative 2, 3, 0. And finally 0, 0, 2, negative 3. Okay, and simplifying this, we can make this a 1, negative 1, subtract it here, 0, 4, 2, this becomes a 2, 1, add it to row 3, add row 2 to row 3, 0, negative 1, so 1, negative 3, and we can subtract 2 row 4s from row 2 to give us 0 and 7, yuck, and subtract row 4 here, 0, 3. Okay, so looks like we should be getting, I don't like that 7. That 7 does not seem right. Oh, it's in the subspace. All right, I read it. It is the subspace. We gotta solve that all over again. God damn it. 0, 2, 1, negative 1. Sorry about that. 0, negative 2, 3, 0, 0, 2, nope, 0, 0, 2, negative 3, and then we're checking if 1. Oh, yeah, no, that ain't in the subspace. We can just see that. Could have done that the whole time. Look. We have a constant term here. There are no constant terms here. There's no way that polynomial can be in that subspace. We can't form it from any combinations of those. So any of these answers with 2 in them is wrong. And this is linearly independent for all real values A. Kind of doubt it. But let's check. 1, 1, 0, 1, A, 3, 1, 2, 0, 1, negative 1, 1, and 0, 0, A, negative 1, 2. Did I write all those correctly? I think I did. Okay, let's copy that over and solve it. Subtracting row 1 from row 2, we get 0, 3 minus A. Okay, subtracting row 1 from row 4, we get 0 and 2 minus A. What else can we do? Let's subtract 3 row 2s from row, 3 row 3s from row 2. That'll get rid of that 3. Subtracting 3, so we're adding 3 here to 4, adding 3, A plus 3. Okay, we're getting vaguely somewhere. Let's see. Let's subtract 2 row 3s from row 4. That'll get rid of that. Make this a 3. Make this a 5. Okay. We're close. We're close. I can feel it. Let's subtract row 4 from row 3. That will add an A here. Make this into a 1, subtracting 3 and subtract 5. So A minus 2. Actually, that doesn't particularly help. Well, we have a pivot position here, a pivot position here, a pivot position here. We would like a 4th one. How are we going to get that? Oh, let's subtract 3 row 2s from row 4. That'll give us 0. I said subtract 3, right? Yeah, okay, subtracting 3. So negative 3A, and then that 2 times 3 plus 5, so 11 there. Yeesh. I'm going to line this up better. Negative A. What should we be doing here? Let's add row 2 to row 3. That gives us 0 and A minus 3. And I feel like we should be able to do something with this. Linearly independent for all real values A. Because really, I'm just looking at these two right here. Let's flip this to an A, 3A minus 11. Let's subtract 3 row 3s from row 4. We're 45 minutes in. A minus 3 minus 3A, and then plus 9 is negative 2. You just want one of these to be equal to something else, please. And I'm not getting it. Which I think just means that these 2 rows are linearly independent, thus the whole thing should be linearly independent. And that should be true. And now we got to go back to number 1, which I was unsure about. So 6, 1, 5, 3 is in the subspace of these 2 by 2 matrices. Okay. Since we're just dealing with linear combinations, let's express these as vectors where this is the first position, second, third, fourth. So we have 2, 3, negative 2, 3, negative 4, negative 1, 0, negative 1, 2, 1, and we're seeing if 6, 5, 3, 1 is in that subspace. We can change this to a 1, 3, add it to row 4, get a 1, 4 there. We can subtract 2 of those. Minus 8 is negative 5. Add it here, we get 0, 9. That's 1, 3, which we can set to 0, 0. Ooh, is a free variable bad? I think a free variable might be pretty bad. Yeah, and look, 1 and 3 don't really mix with this. Yeah, look, if we add 4 row 1s here, we're going to get 0 and plus 12, so 7, 0 combinations of those equals 7 of that. Yeah, that's no good. So it should be 3 only. Yuck. Yuck, yuck, yuck. 12. Let A and B be 4 by 4 matrices such that A is that and the determinant of B is 6. What is the determinant of A times B inverse? Well, interesting question. The determinant of two matrices multiplied together is the same thing as the determinant of A times the determinant of B inverse, and the determinant of B inverse is the same as 1 over the determinant of B. So that gives us 1 over 6 here. And now we actually have to find the determinant of A, which looks like it's going to be a pain. Yeah, that looks terrible. But I guess we can try to put it in upper triangular form. 2, 5, 0, 4. Let's see, we're 47 minutes in. 3, 8, 11, 5, 4, 6, 3, 8, 2, 9, 0, 4. This is a much crappier determinant than they usually make us take. So we can't multiply any rows by any factors or flip any signs or anything, or else we have to keep track of that, and I don't really want to. We can only subtract factors of other rows legally. So let's subtract row 1 from row 4. That'll give us a 0, a 4, and a 0. Okay, that's interesting. Let's subtract 2 row 4s. Well, we can use row 4 to multiply it by some arbitrary constants to get rid of all of these entries. That's good. Let's subtract 2 row 1s from row 3. That gives us 0 and 0. That's also good. In fact, at this point, we know that the determinant of this should be the same thing as the determinant of this. So if we know that plus, minus, plus, minus, plus, if the sign of this 4 position is plus, we can take 4 times the determinant of the matrix formed by crossing out the row and the column of 4, and then plus, minus, if the sign of that 3, oh, nope, can't really do that yet. Yeah, actually, I'm just going to keep going here and see if we can make any more simplifications. Can we really, though? I don't know. I think I'm okay with that. So we have plus, minus, plus, minus, plus, minus, plus. Yeah, and then we have this matrix here, 2, 3, 0, 0, 11, 3, 4, 5, 0. And yeah, we can do that. We can take plus, minus, minus 3 out, so we have 12 outside, and then the matrix 2, 3, 4, 5, which gives us a determinant of negative 2, 10 minus 12, negative 2 times 12 is negative 24, divided by 6 is negative 4. Okay, hopefully that's right. 13, consider over 6. Okay. Consider the equation AX equals 0, where A is a 5 by 7 matrix. Which of the following statements is or are true? Ax equals 0 has infinitely many solutions. Okay, 5 by 7. 5 here, 7 here. That means that our output space is lower dimensional than our input space. So yeah, there must be an infinite number of vectors smushed onto 0. So 1 should be true. The matrix A has a rank less than or equal to 5. Yeah, I agree with that because we can only have a pivot position for every row that we have here. So yeah, max our rank can be 5. That's why our null space has to be at least 2-dimensional. Yeah, okay, and that helps us solve 1 too. That reinforces what we already said. So rank less than or equal to 5, I agree. The associated linear system has 2 free variables. Nope, doesn't have to. At minimum, it would have 2, but doesn't have to have exactly 2. It could have way more than 2. If our rank is only 1, like just like this less than or equal to implies it could be, we would have 6 free variables. So nope, untrue. 1 and 2 should be correct. 14, let M 3 by 3 be the space of all 3 by 3 matrices. Let H be the subspace of M 3 by 3 consisting of all matrices with entries given there such that A times 1, negative 2, 0 is 0, 0, 0. What is the dimension of H? Okay, well this is the solution to Ax equals 0. It's solved for 1, negative 2, 0. And that implies that since Ax equals 0 has solutions other than the trivial solution, that the null space is, in this case, it's looking like it's, would that be 3-dimensional or 1-dimensional? I'm not exactly sure. What is the dimension of H? 1, 3, 6, 8, 9? Yuck. Okay, well, let's think about what this means. So if we have A, B, C, D, E, F, G, H, I, and we multiply it by 1, negative 2, 0, we know that, let's see, this will be A minus 2B plus D minus 2E plus G minus 2H is equal to 0. Okay. I think we can do this. So that subspace has 1, 2, 3, 4, 5, 6 variables that we can vary. Mess around with if there was a slider for each one of them, we should be able to mess with all those and have this still be true. But C, F, and I are free variables, so the total dimension that this could be is 9, but the dimension of H should be 6, given those 6 variables there that all have to, okay, I think that works. 15, for the system of differential, okay, thank God, an easy peasy question. 1 minus lambda times negative 6 minus lambda plus 10 is equal to 0. Lambda squared plus 5 lambda minus 6 plus 10 is plus 4 is equal to 0. Lambda plus 4 lambda plus 1 is equal to 0. And since both of our eigenvalues, we have negative 1 and negative 4, both of them are negative, that means that our origin is an attractor. Okay, perfect. That's the first time in 3 years where the answer hasn't been saddle point. It's usually always saddle point. Okay, let's consider this linear transformation from R3 to R3, where A is a real number. Let's see, is the linear transformation 1-to-1 for every real value of A? Well, it's 1-to-1 if we set up a matrix with these 3, simplify it down, and if we get 3 independent, if our columns are independent, so we're expecting to get 3 pivot positions. A, 1, 2, negative 1, 3, 1, 4, A, 4. A, -1, 4. Okay, let's subtract 2 row 2's from row 3. That'll give us 0, 1, 3A. 1 minus 6 is -5. 4 minus 2A. Ew, that's a little messy. I don't like this. I don't like this at all. Yeah, I'm not a fan. Let's see. What can we do? Can we even get rid of? Yeah, okay. Okay, let's multiply this row by 5. We'll get 5, 15, 5A, and then let's add 3 row 3's to it. That'll give us a 0 here. Adding 3, so plus 12 minus 6A, so 12 minus A. And what can we what can we do with this? Now we can get rid of that too. Okay, I guess we're multiplying this by 5. 5A minus 5 plus 20, and then subtracting row 3, we'll get a 0 here. And so minus 4, 16 plus 2A. This sucks. This really sucks. So we kind of have two similar looking lines. Let's write these out. This says that 5A x1, then we can put x3 over to the other side, is equal to -16 plus, or sorry, -16 plus 2A x3, and then that second line says that 5x1 is equal to -12 minus A x3. If we divide by A over here, 16 over A plus 2, and if we divide by 5 on both of these, we should get let's see, we can set both of these equal to each other, because 5x1 should be equal to 5x1, so -12 plus A is equal to -16 over A minus 2, adding 2 to both sides. Yeah, this won't have a solution for every A. Yeah, no way. Okay, so one's got to be false, I think. The linear transformation is not on 2 for A equal to 2. Oh, well, that would have been good to know. If it wasn't on 2, then it's not going to be 1 to 1. So what they're saying is if A is equal to 2, then our columns here will not span our output space. So 2, 1, 2, -1, 3, 1, 4, 2, 4. Yeah, because we have a column that is a linear combination of another column, so multiply this column by 2 to get that column. Yeah, no, it is not on 2, and 2 is true. And so, by definition, because it's not on 2, actually it could be 1 to 1. Wait, it could be 1 to 1. Interesting. Yeah, it still could be. Okay, 3. The standard matrix for the linear transformation relative to the standard matrix on R3 has rank 3 for all real numbers, A not equal to 2 or 8. Oh, God. Again, I gotta review that. I'm pretty sure our standard matrix relative to this basis would just be what we've written down here. And they're saying as rank 3 for all real numbers, A not equal to 2 or 8. Yeah, so for A not equal to 2, we do have a problem, but for A equal to 8, what would happen here? 8, 1, 2, -1, 3, 1, and 4, 8, 4. Let's simplify this down. Subtracting 3, yuck. I'll do this first. Subtracting 2 row 2's from row 3, we'll get 0, minus 5, minus 16 gives us -12 here. It's already getting messy. Subtracting 8 row 2's from row 1. That will be minus 24, so minus 25. Ooh, there's 5 and 25. And minus 64 is just minus 60. Yeah, okay. 25 times 25, or well, really it's just 60 over 5 that we have to worry about, and that is 12. So, yeah, this has rank 3 for all real numbers, a not equal to 2 or 3. I agree with those two. Is it 1-to-1 for every real value? Yuck. Okay, I'm coming back to this, I promise. But 2 and 3, I'm pretty sure that is our answer. 17, let's find the distance from vector y to the subspace w spanned by these two. Ooh, okay, something I learned recently. Hopefully I can remember how to do it. We just hit an hour in with 7 questions left and a bunch to go look back over. Okay, distance to a subspace. So spanned by those two, we should be able to we should be able to use least squares here, right? So if y is not in the subspace W and we say that A is U1, U2, then the solution to the least square solution to AX equals Y will be A transpose A is equal to A transpose Y. So A, in our case, A is 2, negative 3, 3, 3, 1, negative 1. A transpose is 2, negative 3, 3, and 3, 1, negative 1. And so we need to compute A transpose times A. Whoops, I kind of want to keep a copy over here. A transpose times A. Wow, this is ugly. I need to. There we go. This is A transpose times A. That will give us, let's see, we have a 2 by 3 and a 3 by 2, so we'll get a 2 by 2 out. 4 plus 9 plus 9 is 22. Then 6 minus 3 minus 3. Oh, that's nice. That's 0. Likewise, we will get 6 minus 3 minus 3 here, and then 9, 10, 11 here. Okay, that's looking good. Now, if we find A transpose, which is 2, negative 3, 3, 3, 1, negative 1, and multiply it by y, which is 1, 0, negative 2. This is a 2 by 3 and a 3 by 1, so we will get a 2 by 1. This gives us 2 minus 6, so negative 4, and 3 plus 2, so 5. So we can set up an augmented matrix, 22, 0, negative 4, and 5, 0, 11, 5. An augmented matrix like that. So we get 5 over 11, and since this is 11 and 2, we get 2 over 11, negative 2 over 11 there. And since that should be the vector pointing from the subspace to our point y, we should be able to take the magnitude of that and get something out. So that'll be the square root of 4 plus 25 is 29 over 121. Oh no, that looks terrible. 29's prime. Oh god. Root 29 over 11? Yeah, that's no good. We're going to come back. Let's consider this solution. Blah, blah, blah. We're solving this. Yeah, we can do this. Okay. Negative 7 minus lambda, 8 minus lambda, plus 54 is equal to 0. Lambda squared minus 8 plus 7 So minus lambda minus 56 plus 54 is negative 2 is equal to 0. Lambda minus 2, lambda plus 1 is equal to 0, right? This is the time in the exam when I start to go crazy. So lambda is equal to 2 and negative 1. For lambda is equal to 2, we can solve a minus lambda I, which will give us a minus lambda I, negative 9, 9, negative 6, 6. And blah, 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 we get an eigenvector of 1, 1. For lambda is equal to negative 1, plugging into a minus lambda I, we get negative 6, 9, 9. We can simplify this down to, well, 2, negative 3, 0, 0. We can say that, and we can see that we get a vector 3, 2, like that. So we can set up x of t is equal to c1 times v1 e to the lambda 1t, which is 2t, plus c2 v2 e to the lambda 2t, where that's minus t, and then we can solve this little matrix 1, 1, 3, 2 is equal to 5, 4. Subtracting row 2 from row 1, we get 0, 1, 1, 0, 2. So C1 is equal to 2, and C2 is equal to 1. We're looking for x1 at 2 plus x2 at 2. x1 at 2 will be, so I can write x1 out. That's 2 e to the 2t plus 3 e to the negative t. Did I do something drastically wrong? Why are so many of these answer choices using e to the negative 2? Oh, okay. No, I get it. don't worry. And x1 at 2, therefore, is going to be 2 e to the 4t plus 3 e to the negative 2. Oh, and this isn't t anymore. That's just negative 2. Okay, it's a little sloppy over here, but x2 of t is then 2 e to the 2t plus 2 e to the negative t. So x2 at 2 is 2 e to the 4t, nope, 2 e to the 4 plus 2 e to the negative 2. Add these together, we'll get 4 e to the 4t, sorry, 4 e to the 4 plus 5 e to the negative 2. Okay, C should be good. 19, we got an inner product. We're finding the orthogonal projection of 10t cubed minus 5 onto the subspace spanned by 1 and t with respect to this above inner product. So subspace spanned by 1 and t. So we're going to be taking 10t cubed minus 5 and subtracting from it its projection onto these guys right here. So we'll need let's call this this function, no, not yeah, whatever, h, sure. We're going to need h inner producted with 1 over 1 inner producted with 1 times 1 minus h inner producted with t over t inner producted with t times t. So let's kind of fill in these blanks. 1 inner producted with 1 is the integral from negative 1 to 1 of 1 dt. We'll be evaluating t on negative 1 to 1, so this is just 2. Then t inner producted with t is the integral from negative 1 to 1 of t squared dt. That's t cubed over 3 on negative 1 to 1. That will give us 1/3 and negative 1/3, so we get 2/3. So we can multiply by 3 over 2. 3 over, I'll just put over 2/3. Why not? Okay. Then the more difficult integrals, we are taking the integral of h times 1, where h is 10 t cubed minus 5 multiplied by 1 dt from negative 1 to 1. That's 10 over 4, so 5 over 2 t to the 4th minus 5t. Since this is an even function, on negative 1 to 1, it's going to just give us 0. You know, it's symmetrical around the y-axis, so wait, I think I made a mistake for that other one then, because for t and t, from negative 1 to 1, we had t squared dt, so t cubed over 3 on negative 1 to 1. This will give us t to the 4th. Come on, I'm having a hard time thinking here. Evaluating t to the 4th, because one of these should go to 0. 1/3, negative 1/3. Yeah, no, that should be 2/3. But then t to the 4th. Oh, because it came from t. Yeah, okay. So this t cubed portion of the integral will go to 0 because t to the 4th will give us, yeah, and same. Okay. All I'm saying is I'm not evaluating this. I don't need to, even though I just wasted more time than it would have taken to actually do it. We get negative 5 here and 5. Yeah, so we get negative 10 for h and 1. Negative 10. And then if we are computing h and t inner producted, that's the integral from negative 1 to 1 of 10 t to the 4th minus 5t dt. This minus 5t is, doing something like that. And so, this is a symmetric integral around the y-axis. So this bit is going to give us 0. We can just get rid of it. And we'll get 2t to the 5th on negative 1 to 1. This gives us 2. This gives us negative 2, so we get 4. 4 times 3 over 2. This is 6. This is plus 5. And so we'll get 10t cubed minus 6t. That looks good. Which of the following statements is true? If 2 by 2 matrices A and B have the same eigenvalues with the same multiplicities, then A is similar to A. Okay. B, row operations on a square matrix do not change its eigenvalues. No, that is untrue. Row operations will change the eigenvalues that you get. C, there exists an n by n non-zero matrix A such that every non-zero vector in Rn is an eigenvector of A. There exists an n by n non-zero matrix such that every non-zero vector. So, let me think about this. I don't think so. No, that doesn't make sense. I don't think that works. I hope we find one that's clearly correct, though. D, the numbers 1, negative 1, and 0 can be the eigenvalues of a 3 by 3. Nope, if 0 is an eigenvalue, then it's not invertible. Because that means that there's some vector along which everything is getting squished down. And so the null space will be non-trivial. Okay, E, the matrix given there is diagonalizable. I really, really hope it is. So if we solve this, 4 minus lambda, negative 6 minus lambda, plus 25 is equal to 0. Lambda squared plus 2 lambda minus 24 Oh no, minus 24 plus 25 plus 1 is equal to 0. Lambda plus 1. Yeah, no, this ain't diagonalizable. Whenever you get multiplicities like this in 2 by 2 matrix land, it's not diagonalizable, because what we would want to have happen is when we plug that in, yeah, no, that's not going to work. Okay, if 2 by 2 matrices A and B have the same eigenvalues with the same multiplicities, then A is similar to B. So A being similar to B means that you can write that you can do the whole diagonalization thing. So A equals PD P inverse, and them being similar. So D and A are similar such that you can do that. And so if they have the same eigenvalues, same multiplicities, then A is similar to B. I think that should be true, because we know E is false, we know D is false. C just, I don't like C at all. Yeah, how are you going to have infinite eigenvectors? That confuses me. And then row operations do change. Yeah, so, okay, that should just be close to the definition of similarity, I guess. Okay, 21. A is here, B is here. For what value of k, if any, will make AB equal BA? Ew, yuck. I don't even know how to solve for this nicely. Well, let's just multiply them together. 2, 3, negative 1, 1. Multiplied by 2, negative 3, 9, k. 2, 3, yep, okay. This will give us a 2 by 2 matrix with 4 minus 9, negative 5. Minus 2 minus 3, negative 5. 18 plus 3k, and negative 9 plus k. Negative 9 plus k. Okay, and then we are just switching this up. I really hope that there's a better way to do this that I can find eventually. 4 minus 9 is negative 5. 2, sorry, this is negative 6 minus k, negative 6 minus k. Okay, well, for this to be true, the only value that k can have is negative 1. So, but will that work for the other entries? Let's make sure. We get 6 plus 9, 15. Okay, yeah, that works if k is negative 1. And finally, negative 9 plus k, negative 9 plus k. Yep, that matches. So A should be good. Okay, consider the basis S for R3 given here. Oh, Graham-Schmidt. Oh, yuck. Okay, so normalizing our first basis vector, we'll just have to divide by 1 over root 5. So I'm liking this, I'm liking this, and I'm liking this. These other ones, nope, because we're looking for orthonormal. In fact, this one is probably completely correct, other than the fact that it's not normalized. So worst comes to worst, we're guessing C, and there's a good chance that C is correct. But if we find our second basis vector, that's going to be this guy up here, 0, 1, 2, minus this dot product here, which is 1, divided by this dot producted with itself, which is, we're using the first vector dotted with itself, which is 5, and then we need to multiply by 2, 1, 0. I'm not liking that. Are we sure it's 5? 4, 5, yep. Yeah. I'm going to be more careful here. I need to be more careful. So we're dot producting 1 over root 5, 2, 1, 0 with 40 minutes left, with 0, 1, 2. That will give us 1 over root 5. and then we're dividing that by the first basis vector dotted with itself. So that's 1 over 5 times 2, 1, 0. No. 1 over 5. 1 over 5 times 5. Okay. And then we're dotting this with 1 over root 5 times 2. Not dotting, multiplying. Okay, so we get 1 over 5 up here. That cancels out. Yeah, 1 over 5 times 2, 1, 0. So minus 2/5. So V2 should be negative 2/5, 1/5, 0. And how are we going to normalize that? Well, oh, wait, negative 2. Yeah, no, I wrote that completely wrong. We have negative 2 over 5, and then 5 over 5, so 4 over 5, and 10 over 5. We can get rid of this common factor in here and just change this to negative 1, 2, 5, 25, 29, 30. Yeah, 1 over 30. Okay, I'm seeing that 1 over 30, root 30, so I'm going with C because none of the other ones go that way too. Okay, 23, let's consider this inconsistent linear system. We're finding the least square solution. Can you tell how my voice is just getting faster and faster as I get more stressed out as the exam goes on? Yeah, that's how it goes. 1, negative 1, 1, 0, negative 1, 2. That's A transpose. We're multiplying it by A. 1, negative 1, 1, 0, negative 1, 2. And that will give us, well, 2 by 3, 3 by 2, so a 2 by 2 matrix. 1, 1, 1, that's 3. 1, 1, 2, that's 3. 3 and 5. Am I right about all that? Yep, 3, 3. Okay, that should be good. And then we need A transpose 1, 0, negative 1, negative 1, 1, 2, multiplied by B, which is 6, 0, 0. We should get a 2 by 1 output. Yep, so this is 6. 6 on top, 0 on the bottom. 6, 0. So we can set up the system, the augmented system of these two, which is 3, 3, 3, 5, 6, 0. And as a result, we can subtract. Stop emailing me. We can subtract row 2 from row 1, 0, negative 2, so 1, negative 3, and subtracting 5 here, 0, 15, 1, 5. So our solution is yeah, 5, negative 3. There we go. Almost chose A for some reason. 24, U to the 2019. Okay, we need to diagonalize this thing. That'll make things much easier because this will just be equal to P D to the 2019 P inverse. So 7 minus lambda times 2 minus lambda plus 6 is equal to 0. Lambda squared minus 9 lambda plus 14 plus 6 is plus 20 is equal to 0. Lambda minus 4, lambda minus 5 is equal to 0. Lambda equals 4 and 5. That checks out, right? Yep, okay, looks good. And then finding our eigenvector for lambda equals, not 2, where did I get 2 from? 4. That will be 3, negative 6, and 1, negative 2. So we'll find blah, blah, blah. In the end, we get an eigenvector 2, 1. For lambda equals 5, we're going to get 2, negative 6, 1, negative 3. So we'll get an eigenvector of 3, 1. So we can write A to the 2019 as P, which is made out of our eigenvectors 2, 1, 3, 1 times D, which is 4, 0, 0, 5 times the inverse of this matrix P, which is 2 minus 3. That inverse is negative 1, so we can add a negative outside of everything, and then 1, 2 -1, -3, and this is to the 2019. We can just take this and do 4 to the 2019 and 5 to the 2019. And now computing. We don't have enough space. I want to compute these. Yuck. I don't like this at all. I'm not having any fun. Okay, multiplying these first two out, we will get a 2 by 2 matrix. It's going to be big though. 4 to the 2019 and -5 to the 2019, -3 to the 20, nope, -3 times 4 to the 2019, and 2 times 5 to the 2019. And finally, we're multiplying this by 2, 3, 1, 1 with a negative sign. It gives us a huge, big thing. We have 30 minutes left. Oh, so much to do. Add the negative sign in. This will be 2 times 4 to the 2019 minus 15 times 5, no, not minus 15, minus 3 times 5 to the 2019. Let's see if we just find something, please, something that matches that there. Yes, yes, there's exactly one answer choice that has 3 times 5, because if we factor this -1 in, we'll get exactly that. 3 times 5 to the 2019 and minus 2. Okay, good. Which of the following orthogonal matrix satisfies this? So I learned this earlier today. These columns should be the normalized bases for the eigenvectors from this thing right here, where these are, but that's Q transpose. Wait, so then are we solving that? Ew. Okay, well, worst comes to worst. If this is just the version of the answer choice where they're trying to get us to not normalize our answers, then our answer would be, no, not that. It would be this here. So that's our choice if all else fails. I forget how these expressions work. It should be like I don't like how they write this. This is still hard for me to read. Okay, so this is our matrix inside. Oh, I see. I was reading an equal sign here. So here's our matrix inside here. Yeah, we're finding the, the normalized eigenvectors. So we know that our eigenvalues are 4, 4, and 1. So if we solve for the eigenspace made by 4, we should be good. So that'll give us -1, -1, -1, -1, -1, -1, -1, -1, -1. We can use row 1 to get rid of both of these. So big 0 down there. And flipping these signs, we'll see that we'll get a vector made out of x2, which is 1, 1, 0, and a vector made out of x3, which is -1, 0, 1. And don't you just love it when the answer choice that you just not guess, but educatedly, I don't know if that's a word, that you guessed is right? Yeah. Yep, A should be right. Okay, let's go back to the beginning and correct. Oh, I'm seeing blank questions. This, yeah, I trust myself on that one. How much time do we have? We have 30 minutes, so let's spend it correctly. Hmm. I agree that 2 is true, but is I'm having trouble thinking. If ax equals 0 has only the trivial solution, then ax equals b has no solution. I'm just, when you're just thinking during a test and your mind isn't working anymore, you're just blanking. That's what's happening to me. Um, no, that's not true. Okay, and then 3, is 3 true? No, no, 3 isn't true. Okay, I think we're good on that one then. Blah blah blah. Yeah. Okay. So we got an answer here, and I would go back and actually do the work if I had time. But since we have questions that I haven't actually answered yet, I'm not doing that. Not doing that. I trust myself. The chances of messing up and getting the correct wrong answer, you know what I mean. Getting one of the answers that they put there, I think is low. Okay, this cross product makes sense. There's been a question exactly like that before, and that one worked. Oh, a question we haven't done. Okay, great. Ugh. Two by three. All these are 2 by 3s. So I think what I might have to resort to is just multiplying. So if we multiply this guy by this thing, we should get this thing. 2 by 3. No, sorry, other way around. If we multiply by this thing, we should get that thing. Yeah. So let's multiply this by 1, 1, 0. We get 0. Yeah. So yeah, no, this is incorrect. Okay, I'm liking this. Guessing and checking. Not guessing, but using the answers to our advantage. This will give us -1. No, that's also no good. That's no good. 1, 1, 0. We will get 1. That's no good. We're looking for a -2, by the way. Ooh, this one's looking good. Both of these are looking good. 1, 1, 0. This gives us -2 and 1 on the bottom, but so will this next one. So we got to check our next one. If we use 1, 0, -1, then we'll get -1 plus 2, so 1, and then 0. Okay, that works. But what about 1, 0, -1 over here? This gives us, yep, still the right thing. So we need to check our third. Ooh, this is not a waste of time because we're getting it correct as a result, but 0, 1, -1. We're looking for 1, -1. Yep, I'm getting 1 there, and then -1. Yep, but what if we test it down here? It better not work, because I'm pretty sure we got our answer here that it's D. 1, 0. Yes. Sweet. D is correct. I didn't think I was going to get that one at all. Okay. V, blah, 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 blah. Yep, I agree with that one. K is 1 or 4. Yeah, because we can have the negative area. But that's still really positive area if we're thinking geometrically. Yup. Okay. Okay. Yeah, I think I'm good with that. What is false? Oh, right, this one. This is one we haven't answered. So we found our basis for call A. We found our basis for null A. We know that E is consistent. It's just a shot between these other bases. So let's take B and row reduce it and see if we get 3 pivots. So we have, I don't have space. -1, -3, 0, -1, -1, -1. I'm not reading the right one. This is a -4. 2, -1, -4. Okay, we're going to zoom in and flip the sign on absolutely everything in here. Let's subtract row 2 from row 1. We get 0, 2, 3. Add 2 row 2s to row 3. 0, 3, 6. We get 1, 2. That'll have 3 pivots. Yeah, because this will be 0, -1, 3 pivots. So then I think that will work. That should work as a basis for call A, but will it be a different? Because our input space is 5-dimensional, and we're dealing with a 3-dimensional space, so just because we get 3, all that means is that it is a 3-dimensional space in 5 dimensions, but it doesn't necessarily mean that it's the same. But then what in the world is going on with this basis here where they flip like, I hate this. I hate this so much. How much time do we have? We have 24 minutes. So here's the basis that we got down here for null A. And if we flip, if we flip that and then that and then that, so they've flipped all the first 3 signs. Yeah, what'll that do? That can't possibly still be the null space, can it? Yuck. Yuck, yuck, yuck. I hate this. Like a lot. Okay, let's think about it. For our column space, let's try to disprove this column space in the next 3 minutes. If B is a basis for the column space, so we have our vector -1, -1, 2, our vector 3, -1, -1, and our vector 0, 1, 2. And that's yeah, there's our basis, and that makes a parallelepiped, and everything else, space follows that, and there's our column space. If we use 4, -1, 4, then we'll still have a parallelepiped, and it'll still span R3, and they're all independent, but does that matter? Okay. In the same way, we can go argue that D is not a basis for null A because we got our 2 vectors, and they've flipped the signs on the first 3 components of them. So first 3 components. So yeah, no way. That's no longer the same thing. And I'm guessing because we found 3 pivot positions in B, that this one would also work. So it is a basis for call A because it still spans R3 within R5, just in a slightly different way. Okay, so it should be A and B. Okay, so that means that our answer is D, and all of our other ones are false. Are true, so they're false, if you know what I mean. Yeah, I can remember this one. Hope I remember it. 20 minutes left. The set of all polynomials, blah, 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 blah. Let's try to think about this in a little bit of a different way. Let's say we have, let's rewrite 1 as, I don't know if this is really legal. Sorry about all those emails. xy as long as xy is equal to 0. And this doesn't work. So this will be the coordinate axes, right? This will give us all the x-axis and all the y-axis and the origin, because those are the places where at least one of the variables is equal to 0. But if we add two of those elements together, then we don't get the same behavior. So let's try to prove that. Sorry, and by don't get the same behavior, I mean, like, so we have this vector here, we have the same vector here, add them, we're out of the space, because that no longer fulfills our requirements. So does that work under vector addition? Okay, what's a polynomial for p0 times p2 is equal to 0? Well, the polynomial x minus 2 works, and then if we add that to x times x minus 2, which we know also works, that's x squared minus 2x. Wait, yeah, but then if we plug x equals 0 into here, we plug in x equals 0, we get negative 2. If we plug in x equals 2, ooh, yes! Look at that! Look at that! Oh no, wait, that's still bad. Yeah, if you plug in x equals 2, then we get 0 from both of them. So since either the first polynomial or the second polynomial has to have, so our first polynomial could be equal to 0 for p0. Our second polynomial, or p1 or both, but our second polynomial would have to be equal to 0 for either this one, or both of them, yet again. But there are no combinations of those where adding them together gives you either p0 or p2, where you're not still going to get 0. Okay, so it still should be 1 and 3. I'm still going with 1 and 3. That was slightly a waste of 5 minutes. AB, yep. I'm agreeing with that. 3, God. So I believe my work for 1, and if 2's wrong, then 3 must be right, and we were getting really weird stuff for 3 that seemed to point to it being right. What about 2, though? Did we... Yeah, we solved 2 right off the bat because we have a constant here, and there are no constants in anything down here to make that constant happen. Yeah, so 3 only, I'm okay with that. What about here? Yeah, I believe my math. You know what got me a 64 on a Calc 3 exam last semester? Believing my math. Yeah, I did 2 line integrals in like a minute, and they were both wrong, and I never went back and checked them. 13, x equals 0. 5 by 7, yeah, so the null space has to be 2, rank is less than or equal to 5, so null space is greater than or equal to 2, so x equals 0, yep, and yep, okay, I agree with that. Yeah, this one's weird. Ooh, here, mistake. So H is the null space. It's consisting of all the matrices consisting of all of the matrices such that AX equals 0 for that specific X, and so I'm actually not sure if there's a mistake. I might have just been yelling about nothing. We expand that out, we get A minus 2B plus D minus 2E plus G minus 2H. What's the dimension of capital H? So this has to be true. It's got to be true. And so we have three variables that don't depend on this at all. And as a result, okay, let's think about this in normal terms. So when we're finding the null space, the dimension of the null space is equal to the number of free variables. The number of variables that you can do whatever the hell you want with them, and it won't change whether or not our solution works. So these guys are constrained by exactly this condition here, but C, F, and I are not. They can do whatever they want, and so the span of I'm not sure if this is rigorous enough, but the span of C, F, and I, it forms that subspace. If we wanted the column space, or however they'd write the column space, then that would be different. So pretty sure we made a mistake there. Okay. Yep, attractor, negative, negative. Is 1-to-1 for every value of A. Yeah, and so because 3 is true, it has rank 2 for values of 8, for 2 of 8, 2 and 8, so it's not 1-to-1 because to be 1-to-1, your columns have to be linearly independent. Okay, I'm okay with this. Oh, right. Forgot about this one. We have 14 minutes. The distance from this to the subspace. So we're looking for, I'm not going to do this with least squares. I'm going to get rid of all of this because 29 over root 121, or root 29 over 11 is not right. So we're looking for, let's see, the orthogonal complement is that what we're looking for? I think so. Yeah, if we find y hat, the complement, we're finding 1, 0. Yeah, this is hairy. I might be doing this wrong. Hope I'm not. Minus the dot product, so 2 minus 6, negative 4 divided by 9, 18, 22. Oh, there's our 4 over 22. I'm going to go back just a second. So we got our least squares solution of negative 2 over 11 and 5 over 11. And it looks like we were about to go down the same road and get the same thing. What can we do with this? So this, what is this? Should we be getting a two-dimensional vector? Yeah, we should. So, okay. I think I remember doing this on a homework. We'll take negative 2 over 11 and multiply it by 2, negative 3, 3, and we'll take 5 over 11 plus 3, 1, negative 1, and that gives us negative 4 plus, yuck. How much time do we have? We have 11 minutes. Negative 4 over, I'll factor the 11 out of everything. 11. Having 11, or 1 over 11 is still not particularly good. So we have negative 4 plus 15 gives us, 11 over 11, we like that. And then negative 6, 6 plus 5, it's 11. And then negative 6 minus 5 is negative 11. And then all this is divided by 11. So we get 1, 1, negative 1. And the magnitude of that is root 3. Did I mess one of these up? Did I? What did I do? 4 and 15, yep. 6 and 5 and negative 6 and negative 5. So the distance should be the magnitude of that, 1, 1, negative 1, which is root 3. Am I crazy? 3, 1, negative 1. Oh, God. What is going on? 1, 1, negative 1. What's wrong with that? 15 minus 4, 11. See, here's what you shouldn't do. Just spin in circles, doing the same math over and over again, getting the exact same answer. Positive 5. Because I trust our negative 2 over 11 and 5 over 11, but we're getting root 3. We're getting root 3. So my hunch is that one of these components should be 0. And so instead of getting 1 and negative 1, one of those should be 0, and that'll give us root 2. But just as easily, we could be 1 short and actually get getting... I hate this. Let's come back to 17, but I'm guessing root 2 for now. Yep, happy with that. I'm also happy with that. Yeah. Every non-zero vector in Rn is an eigenvector of A. So even like what? No, I don't like that. That's not, can't be right, right? K is negative 1, yep. Gram-Schmidt, least squares, blah, blah, blah. Happy with all of these, except for number 17. And how are we going to maximize our 8 minutes that we have remaining here? Sadly, I think what we're going to do is recompute least squares, because this should work. If we do our least squares and then plug it in take it as a linear combination of this plus this, then that should work. Maybe the key, wait a second, maybe our least squares, that's finding y hat, and what we really need to do is take y minus y hat, so 1, 0, negative 2, minus our y hat is 1, 1, negative 1 that we found up here. That gives us 0, negative 1, negative 1. There's our root 2. There is root 2 right there. You know what? I'm going with that. What else can we possibly do here? Dimension of h. I really hope that's correct. Well, let's think about that. So if we have a subspace. Yeah, the null space is defined by the free variables. Yeah, that checks out in my head. Negative 4. So at this point, I'm actually gonna call it. I am confident in all of my answers. If things are wrong, more than likely, first off, more than likely, multiple things are wrong. But past that, I would guess that my overconfidence in my own algebra will lose me some points, like it tends to do. Like on questions like this, missing a negative 1 is kind of the end of things. Yeah, and I just don't have the time to go back and check stuff like this. But hey, I don't know whether people are actually going to watch this. It was a very good excuse for me to stress myself out for 2 hours, though, that's for sure. I don't even know if I'm going to upload it. But hey, I'm going to go use the bathroom, and then we're going to go through these answers. Okay, time to go over our answers. I can get them pulled up here. Somewhere on my desktop. Yeah, there we go. Okay, you can go look at them yourself, but I'm just gonna. Whoops, it's the wrong desktop screen. There we go. I'm just gonna read them out as we go. As we go through, gotta get rid of that. 1 is D. That's correct. Let's see. We're gonna use a big green highlighter. 2 is A. That's correct. Yep, that's we weren't too unsure about that. 3 is C. 4 is B. 5 is D. 6 is B. Let's see, are any of these crazy? Haha, look. 5, the one we kind of sort of guessed on. 7 is E. Oh, good. Okay, that was a kind of sketchy one. An even sketchier one, though. 8 is, yes, D. Sweet. Sweet, sweet, sweet. 9. Oh, there it goes. 9 is E. So this is incorrect. There we go. It was going to happen. But let's see. So the answer is 3 only. Okay, I'll have to go back over that and see why that is wrong. Interesting. 10 is B. Sweet. 11. Ooh, this one could very easily be wrong. Oh, but it isn't. 11 is D. Oh no, 12 is. Look at that. Look at that. What was I saying about missing a negative sign and getting something wrong? 12 is D. So that is incorrect. Wait, what did I just say? No, 12 is B, not D. So yeah, we do have it wrong. 13 is A. 14, oh, we changed it to the incorrect answer. 14 is C. It is 6-dimensional. Ugh, that's sad. Yeah. Okay, that's too bad. I think I was thinking about it in a little bit of incorrect. Well, obviously because I got it wrong. Whatever. A is correct. Yep, we're fine with that. 16, yep, is D. 17 is A. 18 is C. 19 is E. Really? Really? No! Look what we did. They wanted the orthogonal projection, not our original H minus the orthogonal projection. That's what we did. They just wanted the so all of our math was correct, but we did 10t cubed minus 5 minus 6t plus minus 6t minus 5, and so okay, that's a little heartbreaking there. 20. Ooh. Ew. 20 is C. Let's see. There exists an n by n non-zero matrix A such that every non-zero vector in Rn is an eigenvector of A. I mean, the identity matrix was floating around in my head, but what in the world? I'll have to go back and figure that one out. 21. 21 is A. 22 is C. 23 is B. A. Whoops, that's the eraser. And oof on the last one. This one is B. Although I thought we had this one. Worked out for the eigenspace, blah, blah, blah. How are they getting 1, 2 there? I'm not particularly sure. 25b. You know what? When I just put this big 0 here, I bet I was wrong. Let's go solve it quickly. 1 minus 1. Wait, this is for 4. Oh yeah, okay. I just got a -1, 1, -1, 1, -1, 1, -1, 1, -1. So we can definitely use this to cancel this out. Yeah, we can use that to cancel that out. How in the world are they getting -1, 1, and 2? Yeah, I don't understand that. How? Because, ugh. Okay, well, this is for me to go over in my own time, but we got, what is that, 5 wrong? No, 6. Yeah, 1, 2, 3, 4, 5, 6. So there's a perfectly good example of one, how it's hard to do these. It's really, these things are hard. It's not like I walk up and record all these on the first try. Um, I did not, and also it's a good show for how you can think that I thought I probably had 1 or 2 wrong. Um, you can think that, and then, yeah, definitely have way more. Ugh, that's kind of sad. Not really sad, but okay, I'm going to go figure out why these are wrong.